Will China pull ahead with battery technology? Are we on the brink of a battery revolution? As electric vehicles surge in popularity, the quest for a more sustainable, accessible, and cost-effective battery solution intensifies. For years, lithium-ion batteries have powered our most advanced devices, from smartphones to electric cars, due to their remarkable efficiency and energy density. But now, with lithium's limitations becoming increasingly apparent, including scarce supplies, environmental drawbacks, and fluctuating costs, could sodium-ion batteries, abundant and economical, be the key to powering the future of transportation? The shift is already beginning. Are you ready for what comes next? Sodium-ion batteries are emerging as a formidable contender, promising to redefine the power dynamics of future mobility. This shift is fueled by the need for more sustainable and economically viable battery technologies. As the electric vehicle market continues to expand, the development of sodium-ion batteries could potentially alleviate the pressures on lithium resources and offer a more balanced approach to energy storage. Sodium-ion batteries utilize sodium ions to transfer charge. Sodium, an element abundant in the Earth's crust, offers a compelling advantage over lithium due to its availability and cost-effectiveness. Structurally and chemically similar to lithium-ion batteries, sodium-ion batteries could be integrated into current manufacturing processes with minimal adjustments, making them an attractive alternative for industries looking to reduce dependence on lithium. The relevance of sodium-ion technology extends beyond mere cost savings. These batteries are less prone to fires and are considered safer than their lithium-ion counterparts. Additionally, they do not require cobalt or nickel, metals that are not only expensive but also fraught with geopolitical and ethical issues. This aspect alone significantly enhances the appeal of sodium-ion batteries, aligning them more closely with global sustainability goals. The entry of sodium-ion batteries into the market is timely. As the global economy pushes toward greener alternatives, the automotive industry is under pressure to adopt more environmentally friendly technologies. Sodium-ion batteries offer a promising solution that could help accelerate the transition to a low-carbon world. Their development is not just a technological innovation, but a potential pivot towards greater energy security and sustainability. One of the most compelling advantages of sodium-ion batteries is the relative abundance and cost-effectiveness of sodium compared to lithium. Sodium is the sixth most common element on Earth and is more than 1,000 times more abundant in the Earth's crust than lithium. This vast availability translates into a significant cost advantage. For instance, in early 2024, the price of sodium carbonate was approximately $290 per metric ton, starkly lower than that of battery-grade lithium carbonate, which could exceed $13,000 per metric ton. This disparity not only makes sodium-ion batteries more economically viable, but it also ensures a more stable supply chain, which is less susceptible to the geopolitical tensions that often accompany rare and valuable resources like lithium. Sodium-ion batteries offer several environmental benefits over their lithium-ion counterparts. Firstly, the mining of sodium imposes a lower environmental burden due to the element's abundance and the less invasive techniques required for its extraction. Furthermore, sodium-ion batteries do not rely on toxic heavy metals such as cobalt and nickel, which are pivotal in lithium-ion battery manufacture and are often linked to serious environmental and ethical issues, including pollution and exploitative labor practices. Economically, the adoption of sodium-ion technology could lead to significant savings in raw material costs, which constitute a large portion of the final cost of battery production. These savings could be passed on to consumers, potentially lowering the price of electric vehicles and other battery-dependent technologies, thereby accelerating their adoption and the attendant environmental benefits of reduced fossil fuel dependence. As of 2024, sodium-ion batteries have begun to find their place in various markets, primarily in low-energy density applications where their lower cost and greater safety profile offer the most benefits. For instance, Chinese car manufacturers like Chery and the JAC Group's Yiwei brand have started incorporating sodium-ion batteries in small urban electric vehicles. These applications benefit from lower range and power requirements, making them ideal candidates for sodium-ion technology. Additionally, stationary energy storage systems, which do not require high energy density, are increasingly using sodium-ion batteries to store wind and solar energy, thus supporting the grid during peak demand times or intermittencies. The economic feasibility of sodium-ion batteries becomes particularly clear when comparing the costs of sodium carbonate and lithium carbonate. With sodium carbonate priced at roughly $290 per metric ton and lithium carbonate soaring at over $13,000 per metric ton, the raw material expense for sodium-ion batteries is dramatically lower. The manufacturing process for sodium-ion batteries, while similar to that of lithium-ion batteries, includes some distinct steps that leverage the unique properties of sodium. The process begins with the production of sodium-rich cathode materials, typically sodium cobalt oxide or sodium manganese oxide. These materials are synthesized through a process that involves combining sodium salts with other chemicals and heating them to high temperatures. Next, the cathode material is ground into a fine powder and mixed with a conductive agent and a binder to form a slurry. This slurry is then coated into a current collector made of aluminum foil, after which it is dried and compressed. This anode, usually made from hard carbon, undergoes a similar process. These electrodes are then assembled into a cell with a separator and electrolyte added to facilitate the movement of sodium ions between the cathode and anode during battery operation. Finally, the assembled cells are sealed and undergo several charging and discharging cycles to activate them, a process known as formation. Once formed, the batteries are tested for performance metrics such as capacity, charge retention, and cycle life before being shipped for use in various applications. Research and development in sodium-ion technology have been vigorous, aiming to overcome the inherent challenges of sodium-ion chemistry and enhance its performance to meet commercial standards. Innovations include the development of novel cathode materials that offer higher energy density and stability. Researchers are also exploring the use of advanced electrolytes that can operate at higher voltages and provide better ion conductivity. Another significant advancement is the improvement in the anode materials. Hard carbon, which is the standard anode material for sodium-ion batteries, is being optimized to increase its storage capacity and efficiency at intercalating sodium ions. These technological advancements are crucial for enhancing the overall efficiency and viability of sodium-ion batteries in competitive markets. As far as challenges in energy density and physical dimensions in sodium-ion batteries, despite their advantages, sodium-ion batteries face challenges related to their energy density and physical dimensions. China has positioned itself as a leader in the development and commercialization of sodium-ion battery technology, leveraging its robust manufacturing capabilities and significant government support. China has rapidly advanced its sodium-ion technology to practical applications, notably in the automotive sector. Companies like CATL, a global leader in battery production, have started mass production of sodium-ion batteries, supplying major Chinese EV manufacturers and setting a precedent that other nations are hard-pressed to follow. While sodium-ion batteries offer promising advantages, they are not expected to replace lithium-ion batteries entirely in the near future. Instead, they are likely to coexist, serving different niches within the broader battery market. Projections suggest that by 2030, the market for sodium-ion batteries could be worth $920 million, whereas lithium-ion batteries will continue to dominate, with a projected market value exceeding $270 billion. The distinct characteristics of each technology suggest complementary rather than directly competitive roles. Hey, that's going to do it for today's video. Please make sure you hit that subscribe button for more videos like this.